我这门课是那个材料热力学。好，那照理讲应该是你们材料系的话，大二的第一门必修，应该是第一门必修课嘛。对。然后你们有收到那个系上寄给你们的 email 吗？有啊。他们有跟你说这门课是英语授课吗？对。那理论上应该是要英语授课啊。那等一下我们可以先试看看，就是这个，因为如果这门课英语授课的话，基本上我在学校里面就没有中文授课的课程。那然后用中文讲话当然是，大家赶快入座。用中文跟大家沟通的话，当然是比较方便一点。那你们有人听不懂中文的吗？有没有听不懂英文的？用英文授课会让你们其实我不知道，至少以往在大三、大四还有研究所的选修课用英语授课，他们评价都不是特别的，应该说会觉得吸收的程度会有限，所以就有同学会每一堂课就录音，然后每一堂课录音之后呢，回去再重新复习一次。那我觉得这样还蛮痛苦的，对，所以我们就看情况。那今天的话，反正我会先 go through 一些东西，反正今天这学期第一堂课而已。那材料热力学对大家来讲应该又是比较简单的一门课，所以我们先试看看，就是有的时候用英文，有时候用中文这样子。那最好的状态当然是说，其实理想的状态就是我想象中的英语授课应该是说，比方说我用英文讲，那比方说旁边两边有字幕，你知道吗？就是同步的那种口译翻成中文，这个是最理想的方法啦。就各位如果去那个歌剧院，或者是还是国家戏剧院，就听过歌剧或者是歌仔戏的话，因为现在懂台语的人越来越少，基本上台上在表演的时候，两边都有字幕，可是因为我们这不是先准备好的台词，所以没有办法这样做。那所以基本上先跟各位讲，就是这个是英语授课。如果你们觉得就是有比较多问题的话，我觉得可以尽量跟系上反映，因为这是学校的一些 policy， 就觉得说我们应该有更多英语授课。可是我觉得前提是说，如果我们没有国际学生的情况下，用英语授课，当然不是一个特别好的一个政策。那其他课程，比方说以前有些课程它有少数的这个外籍的学生的话，那当然要用英语来教这样子，那没有办法。所以基本上，我们第一周基本上就会开始上课，只是说前面几份这个投影片有几个 lectures，跟各位之后用到课本的东西不太一样。那这是我一贯的做法，就是我会先用比较快的方式，让各位快速的了解，就是热力学从第0、第1到第2定律。我们热力学基本上有3个定律，那0、1、2。那其实还有个第3定律，可是这个它到底是不是一个定律，这我们就我们之后会讨论。那所以一开始这学期一开始，其实我们就会先 go through 就是这个 four laws of thermodynamics。那其实热力学其实就是驱动宇宙进化的一个或演化的一个的 backbones。所以这边就写 the four laws that drive the universe。那这同时也是我前面这几份投影片背上的这个书的这个 title。那所以我们第一堂课讲的其实就是这个第0定律。
可以开吗？
这边吗？这边不知道为什么它没有开，等一下 它显示是已经开了啦，应该是说它没有连上去吗？你再等一下好了。对，因为它这个不知道是说它没有显示，还是因为它讯号可能只接到同一个。基本上最重要的就是说，各位为什么要学热力学？So why the thermodynamics？ 这边讲的是这个1977年的这个诺贝尔化学奖得主他讲的一段话，然后发表在这个 Science 上面。那Ilya Prigogine 他是研究的主要是这个非平衡态这个Thermodynamics 哦。那他在这一篇叫做 Time Structure and Fluctuations 里面提到的，就是说 It's a remarkable fact that the second law of thermodynamics has played in the history of science a fundamental role far beyond its original scope。所以特别抓出来讲的其实是这个热力学第二定律。Suffice it to mention Boltzmann's work on kinetic theory， 就是包含了这个Boltzmann 的这个理论，动力学。那还有这个 Planck's discovery of quantum theory， 普朗克提出的这个量子理论，还有 Einstein theory of spontaneous emission， 各位也学过这个光链效应，这个自发的这个emission which were all based on the second law of thermodynamics。就说你概括来说的话，其实他们都是算可以包含在热力学第二定律的范畴里面。OK， 所以简单来讲就是it's all about everything。所以热力学的应该说你学热力学的话，各位在往后这个学期会常常碰到很多几乎都是一些计算。那可是其实它背后的意义其实蛮深远的。等一下会提到一些例子。等一下，为什么它不完？那对于我们这边是材料系，主要是材料系的学生嘛，有没有外系的学生的？有没有外系 ？OK， 1、2、3，应该不多。那因为基本上这门课还是属于材料热力学。那当然在上半学期，应该说上学期这边各位会碰到了，其实跟一般在其他系会碰到的热力学不会差太远。甚至跟各位普物如果已经学过热力学这部分的话，其实是差不多的。所以有点像是在帮大家复习普物的时候，你们学到的热力学。那在这学期的最后面，可能就会碰到一些是跟下学期比较有关的。那下学期其实是跟材料系的东西会比较相关，比方说各位会碰到相图。所谓的相图就是说，我们这样有2个轴，一个轴是压力 P 用 P 表示，一个轴是用温度 T 来表示。那在这里面的话呢，我们可以看到说，我们知道在不同的温度跟压力下面，物质它会有不同的相，它有不同的状态，它有不同的相，所以我们可以用这样一个图去把它区分开来，可以按图索骥，就是说我们现在处在的温度跟压力的时候，我们的物质，我们探讨了这个系统大概会在什么样的状态。那同样的，这个可能各位在采导的时候就有看过这样子的这个相图了，那我就不再多说明。比方说这是成分，然后这是温度，然后你可以去看它有不同的相。那我们刚刚看到这个是比方说单项，就是这个是单一个物质它所有的这个相图哦。那当然还有这所谓的合金的话，比方说以这边来看，它有个3元的合金，也不知道它为什么会跳，就是3元合金。那你在掺不同比例的时候，它应该处在哪一种 phase？ 那这个就是热力学最重要的地方。到最后尤其是下学期的时候，你们会遇到的就是用热力学去算这些相图。那我们材料系有很多课，其实基本上都是跟这些有关。OK， 那 这个像图呢，对我们来说，其实是我们去了解材料的平衡状态的时候的一个现象，就是说，热力学探讨了其实不是一个 dynamics 的行为，而是一个 equilibrium 的状态，就是当我们达到所谓的热平衡之后，我们系统将处在什么样的一个位置，或者处在什么样一个情况？这个是热力学可以去解决的。OK。那对于我自己来讲，我认为热力学在看的其实就是让你比较能够去了解，你想要探讨的系统是什么，你的周遭的环境到底是什么。那这个你的整个这个加起来，total 来说，这是个 universe 到底是什么样一个形式 ？OK， 所以在探讨热力学的时候，不管是在我们现在会碰到的这个古典热力。还有之后，其实我们会提到，就是补充的这个统计热力学来说，最一开始需要去定义的，就是说你现在探讨的系统到底是什么，你的 system 到底是什么东西 ，and what is your surroundings， 然后你才能决定说你的 universe 到底是怎样。比方说，我可以把这间教室当成是我的这个system。所以你们就包含我自己，我们就是在这个 system 里面的这些，比方说是 particles。那 surroundings 的话，要看你要怎么样去界定。我可以说就是这间教室以外的所有东西我们把它叫做 surroundings， 就是我们的环境。那这间教室以外的所有的东西包含我们自己加起来就我们这个 system 加起来就是这整个 universe。对，所以取决于你怎么样去界定你的 system 跟 surroundings， 我们有不一样的讨论的方法。那这 system 我们等一下也会看到它其实有不一样的区分，就是说这个它可能有所谓的isolated， 就是完全封闭的这种系统，或者是closed system， 或者是这个 open system。那取决于你跟外界怎么样去进行能量或物质的交换。那基本上热力学在探讨的就是这些东西，所以我觉得各位可能通常需要一开始比较需要去注意的，或比较常去忽略的，因为我们材料热力学这本书，到时候你会发现说课本其实蛮着重在从第2章过后蛮注重在这个计算，所以这个东西可能在前面第1章的时候我会建议各位先搞清楚。因为这个跟各位如果之后要做其他的这个research， 或者是跨到其他领域去做研究的时候，这些定义是通用的。比方说你跳到物理系或化学系去做，之后去做你的这个graduate studies，基本上这些尝试都用得到。OK， 所以我们这个学期基本上会讲的，会 cover 这些主题啦。一开始我们会讲这个的 zeroth law of thermodynamics，first law、second law and third law。所以这就是我讲的，我们这个课程安排上面不是一开始就从哪本书开始的原因，就是因为其实先跟各位把这4条定律先带过去，我想会让各位比较有清晰的一个图像存在，所以我们会从这个4大定律开始，很快速的带过去。那接下来我们回到这个课本上面的时候呢，课本一开始当然还是从这个first law 开始讲，zeroth law 跟 first law 啦。那 first law 最重要的一个地方就是它其实就是一个能量守恒的概念。那讲完这个 first law 之后呢，我们就会开始介绍从课本的第3章开始，如果没记错的话，就是讲这个 entropy。那这个 entropy 的概念，你们在普物的时候应该也有，普物或普化应该有学过吧？有或没有？有 ，OK， 对，所以基本上这个东西概念应该是有，所以只是我们会比较仔细的下去讲，所以你可能如果觉得太 detail。OK， 你没有想要了解的那么清楚，或觉得对你以后没有什么太大帮助的话，你可以自己带过去这样子。不过基本上entropy 这个它其实有很 明确，就是根据这个热力学第二定律，它是有很明确的这个机械式的定义。那我们有这个 classical， 就是克劳修斯的这个定义，然后还有这个 statistical Boltzmann 的这个解释方法。所以 entropy 取决于你要看的是一个巨观或者微观的一个效果，它会有不同的解释。那前面这部分其实就是我们可能第一次期中考的范围。那接下来我们会提到一些这个 auxiliary functions， 还有 Maxwell relations。那其实对于热力学来说，它其实提供了很多不一样的计算能量的方法，还有不同的能量的形式。那根据这个有一些人的讲法，其实就是《Four Laws of Thermodynamics》这本书的作者 Peter Atkins。如果你们是有化学系背景的话，当然就知道那个 Peter Atkins 写过很多这个化学的书的教科书。那基本上他的看法是，这些auxiliary functions 就是我们用来计算能量的这些函数，就像是不同的记账的方法。OK， 就是你想要去算什么东西，那化学家、物理学家就定义出这些不同的函数。比方说 U 是这个 internal energy 内能，然后 H 的话是这个enthalpy， 中文应该叫含。那 A 的话是这个Helmholtz free energy。那取决于你是从物理系那边来的，或化学系那边来的。这个Helmholtz free energy 的符号可能不同，有的用 A， 有的用 F。不过在我们这本书里面，它是用 A 来表示。那再来就是这个 Gibbs free energy G。那这些后面这两个就是 free energies，其实是可以告诉我们，就是系统在不同的情况下，它能够做的功最大大概有到多少。OK， 那这个是热力学蛮重要的4个我觉得4个这种所谓的记账的方法，或者说计算能量的方法。那在上半学期的话，我们会着重在这个，比方说 U 跟 H， 这个大概在前面几个礼拜我们就会看到，然后在课本里面你就会碰到很多这方面的计算。那在到第一次期中考过后，我们可能就会开始在看这个Helmholtz free energy 跟 Gibbs free energy 这2种自由能，还有我们为什么需要自由能来定义这些能量。然后另外一个很重要的就是 heat capacity of solids。那这边这个东西其实在我们这一本书里面其实是蛮奇怪的，就是说它虽然提到了heat capacity of solids， 然后提了这个 Einstein 跟 Debye model， 可是它并没有很细节的去推导，就是说它到底怎么来的。所以这边我可能会花比较多一点时间go through 就是这个 Einstein model 跟 Debye model， 因为这个东西各位以后在固态物理或者是其他课里面，或普物我不知道你们有没有已经学过了，就是都会碰到，就是说你怎么样去推导出这个热容量，或者说你说这个固体的比热它跟温度的关系为什么会是长那个样子，那这个是非常重要的，所以可能会花比较多时间在讲这个。那在你们的课本里面，它其实提到这个东西，它只是要把这个 heat capacity 的概念抓出来而已，就是heat capacity 对于固体来讲，它可能跟温度有关，所以它会是一个温度的函数。所以你在做一些计算的时候呢，基本上需要得到这个关系式，然后才有办法去做一些运算。所以它的出发点其实是这个样子。OK， 那有了这些东西，有一些这些information 之后，你就可以去看这个去探讨one component system 的一些项的变化。那最简单来看，各位其实在普物或普化一定会碰到就是水，水是我们人类生活中最重要的一个应该说物质，所以一开始我们会碰到的一定是水，那水讨论完之后呢，我们可能就会去看这个气体。那气体的部分，一开始其实我们一定会先讲 ideal gas， 就理想气体。那可是在热力学，尤其是在你们这个阶段热力学比较重要的反而是这个 real gas， 就是非理想的气体。所以 在书里面当然很多计算的一些题目，当然都是基于这个non-ideal， 就是非理想的这个气体。那这本书我们这学期大概就是会停在这个应该是第6或第7章吧。那所以就是这本书一半附近。那基本上就是会 cover 上面这些东西。那我们的书里面其实在讲 entropy 的时候，有稍微提到一点点这个statistical mechanics， 可是我自己是觉得他讲的不够仔细啦。那而且其实下学期的时候，你们在上材料热力学2，如果还是高正宏老师上的话，基本上他又会再把前面这部分再复习一次，所以我会花大概1-2周的时间，把这本书上面没有的比较偏向统计热力学的部分，再讲的稍微仔细一点。当然，如果各位想要更深入的话，可以去 take 那个，比方说物理系或物理所的统计热力或统计力学。那我觉得这个都看各位之后的修课，或者说想要走的方向。不过统计力学或统计热力的一些概念，其实我是觉得还蛮重要的。那如果时间允许的话，可能才会讲这些异于这个 classical distribution 的一些function 那这个是比方说 Maxwell-Boltzmann， 各位知道就是这个古典的这个 particles， 它的这个能量或者是速度的这个分布然后还有所谓的 Bose-Einstein、Fermi-Dirac， 就是取决于你的 particles。如果你探讨的是不是 classical， 不是古典的粒子的话，你需要去考虑到这个所谓的 Bose-Einstein 的 statistics， 或者是 Fermi-Dirac， 取决于你探讨的是boson 还是 fermion， 就玻色子或者是费米子。比方说电子的话，就是费米子。那光子啊这些这个就是所谓的 boson。那我们会探讨如果时间允许的话，会探讨的 ensembles， 就是系众的概念。系众就是写一下，这不知道是台湾这边的翻译还是应该是中国大陆那边的翻译。那 ensemble 的意思就是各位玩弦乐的话，应该就知道是一个像集合的一个概念。那 ensemble 其实就是系统的综合，a collection of systems。所以不同的 ensembles。会对应到，其实我刚刚有口头上面稍微提到了这个isolated， 还有这个 closed system， 还有这个所谓的这个 open system， 它们对应到其实就是不同的这个 collection of systems， 不同的 ensembles。那它们的这个 partition function 也会不一样。OK， 那 partition function 是什么？我们可能要等到学期末，才会看到。好。那接下来是些这个public announcement， 就是如果你还没有看这个，就是因为你们是材料系的学生的话，这个是必带，所以其实你可能也没有看这个课程大纲，还有我们这个课程的需求。所以课本的部分主要有2个，第一个应该说主要是就只有一个啦，就是 Introduction to the Thermodynamics of Materials，这是 by David Gaskell。那这本书其实已经用了10几年了吧，至少从我还是在大学部的时候，就是这本书了，然后到你们的学长姐，然后现在，那它虽然有改版，东西并没有很大。那我每一年都要讲，他常常会把错的东西改成对的，可是又把对的东西改成错的，所以每一年其实就是像一个 treasure hunt。就是你们去找这本书到底有哪些地方有错。那很恐怖的地方就是说，因为热力学，尤其材料热力，你们会花很多时间在做一些计算题嘛。那计算的时候呢，那个数字带多少就很重要。那有的时候它的范例会写一写，它的数字就错了，然后你后面的东西就会很有问题。那所以通常我会尽量帮你们把这些东西identify 出来。那可是我觉得大部分的时候你可能还是要仔细 go through 那些 数字，因为它很有可能在某个地方就带错。然后它的习题的部分呢，很多地方其实你们在网络上我知道可能大家都会找到解答或学长姐留下来的这部分。那有的还会有不同版本，就是解答可能有不同的版本。那不过我建议各位还是自己把东西算一算，这样会比较知道你算的东西到底是对的还是错的。OK， 那另外一本书这个《Four Laws That Drive the Universe》是我刚刚讲这个化学家 Peter Atkins 写的一本书。然后 Peter Atkins 写了蛮多跟热力学有关的，我觉得还蛮有趣的通俗的书籍。那这本书大概只有100多页而已，应该不知道有没有100页，可能就是100页上下。那它其实很快速的就让你去了解0123定律到底在讲什么东西，然后也有讲这其中的historical background。所以我是建议如果各位有时间的话是可以把这本书借来看。那我应该也有这 PDF 档，那我会再把它上传到那个 C 把上面。OK， 所以我们 grading 的方式，跟去年不太一样，或跟以往不太一样。但是其实我从今年开始，我所有课程都变成这个样子。就我以前以往都有作业，可我后来发现作业的版本基本上就是那几个版本，对，就是会真正写作业的大概就那几个人嘛，那所以这个东西就变成不是一个很好的评量的方法。但我知道，就是说作业算是一个保障的分数，就是说你如果有写作业的话，你可能你有 hand in 那张纸，然后 你可能就会得到那个分数。可是你要想想看，就是根据我的统计，每个人最后都拿到接近80-90分，有交作业的话，那在做这件事情的过程里面，其实浪费了大家很多时间，因为助教要来收作业，助教很辛苦，然后助教要改作业，可是这些作业其实它的information 的 content 其实很低，因为它不是你自己生产出来的东西，所以它的知识含量其实非常非常低。那这就其实就是在浪费大家的时间。所以我觉得与其浪费大家的时间，你想想看，他50几个人，假设有20几个人是自己写的，那剩下30个人就是可能是有些不会就抄一下，那其实就是等于浪费了30个人的时间，或浪费了助教去改30分作业的时间。所以倒不如就是我们把所有的测验所有的考核拿到考试来看。那其实因为材料热力学从我那个时候开始，甚至我在国外看到的很多都是考3次。那我自己是认为有点考太多，可是因为我们现在把作业这部分拿掉，所以我觉得考3次其实是还蛮合适的。那第一次 midterm 大概会是在10月下旬，在10月20几号那时候。对，那2次 midterms 大概都是占30%，那期末考的话大概占40%，因为有包含比较多的部分，然后还有包含统计热力学的部分，所以作业我会把题目跟题号放上去，就是课本里面的习题，那些的话，就是我们如果考试里面有出现课本里面的习题的话，基本上就会从那些题目里面出来。所以这个是先跟各位规范起来，所以大家也不用浪费，不是说浪费时间了，就是说你要写习题的话，你就自己练习，不会的话，解不出来可以跟同学讨论，可是我们就不用花时间去把它交上来，然后助教去帮你们改这样子。那有勾选的习题。解答我也都会放上去这样子，所以不用担心。那或者基本上你们从以前到现在，应该都有学长姐 pass 上下来的这些怎么讲，就是解答嘛，所以应该不用太担心。那我们以前这些考试的话，基本上都是跟这个 蛮相关的，就是比方说有60%是出自这个勾选的习题，那剩下的部分是一些跟上课内容有关的部分，对。然后我不会点名，所以你不来我也不会知道。那这也是从以前到现在我的 policy 就是这样，如果你可以不来，然后都考满分，那就是你很厉害，对。然后你如果因为我们毕竟是早上9点课还蛮早的。如果你觉得很累，想要睡觉，你就在宿舍睡觉，在家睡觉就好，就不用来课堂上睡觉，因为来课堂上睡觉也浪费你的时间，你可能也睡得不是很好，对。那你这个年纪可能又很需要睡眠，对，所以我是建议就是如果要来，真的就来上课就来上课，不来上课其实就不要来，因为真的是还蛮累的这样子。然后我们这学期助教是那个詹心怡，是我们硕班的学生，他在那个后面，所以你们如果有问题的话，应该说主要是以前比较常遇到，可能是习题的部分，然后还有这个考试啊，我觉得考试的时候可能问题会比较多一点，就是考卷改完了，可能有些要分数，对，每一年不太一定啊，就是有些人会很想要来要分数，那这个的话就是可能就交给助教去处理，那如果他没有办法解决问题，那可以再寄 email 问我。那他的 office 是在我们实验室，在公众329。office hours 的话，其实是一个蛮重要的一个概念，可是应该说在我们学校，在台湾好像 office hours 不太受重视，所以从以前到现在，我们的 office hour 其实最后都有 announce， 可是到最后会来问问题的人都没有很多。那一般来讲，会遇到的状况是这样，就是考试前1周或2周，然后就会有学生开始寄 email， 然后寄 Facebook 讯息，然后这边再另外一个 public announcement， 就是不要用 Facebook 寄讯息问我问题，对，因为这是很 annoying 的事情，因为Facebook 是蛮 private 的一个地方哦，我不想要就是用这么，比方说你会传简讯问什么，比方说教授问题吗？不会，尽量不要这样做了。我觉得尽量不要这样做，就是有一些问题的话，你可以写 email， 然后如果真的是需要1对1，我们来讨论的话，我们再来约这 office hour 的时间。对，那至少去年的状况是，可能说有2、3个学生他们在考试前有问题，所以我就会set up 一个时间，那就是到 office 来，然后我们再来讨论，看他有什么样的问题，可以帮他解决。对，然后最后是学期末的话，以往没有发生过，在材料热力学没有发生过，可是在其他课程有发生过。如果应该说尽量不要来要分数啊，就是说，比方说有以前遇到过的，就是有拿 A 或是 A minus， 然后他说他要 A 加，那我觉得这个就有点太 over， 就是说其实拿 A 已经很不错了，那用这种方法来要分，就是比方说他会挑说你考卷这边改好像有点不是很 consistent， 对，那他会有各种方法去挑，他说你上课没有讲，对，那现在我们都有录影，好，这学期开始我们都有录影，所以就不会有这样的问题，你就可以去调录影带来看，对，那有凭有据嘛，所以尽量不要来要分数，除非说真的很严重的错误，就是说这个地方大题20分你全部改错了，或者说你期中期末你觉得你都考90几分，可是你期末最后你拿到分数是 B， 那就很奇怪。不过我们在成绩送出之前，基本上我们都会把这个成绩试算的成绩公布给大家看，所以你可以看到你自己的所以不用担心说在 最后送出去前发生什么错误。OK， 所以助教的部分可能就会负责，比方说你们作业有问题或者是这个考卷批改上面有问题，可以去问他。那也是一样不要用 Facebook，不要用 Messenger 之类的，就是尽量用寄 email 的方式，因为这是一个比较 formal 的形式，然后也让对方有时间去反应。好，所以接下来我们就直接进入那个课程的内容 ，OK。所以你们要我用英文讲，还是要用中文说？吕承轩是想要来听英文，是不是 ？OK。I don't know. We can start from here, and switch to English. But that's, so this is my personal opinion. I don't like this policy. So this is on record because someone is recording right now. But I don't like this policy of English teaching because we don't have any native English speaker here. Or if there's any, please let me know. But this is the policy of a university to make this university more internationalized, which I think is kind of stupid. And typically, if I teach this course in English, student cannot get the most from the lecture. And most of the time, I have to slow down. And sometimes I have to teach in English for the first time and switch to Chinese and explain for the second time. And I don't like this to happen here. So I will just slow down, and if you have questions, please let me know. So at the very beginning, I have to go through the timeline of thermodynamics, and this was adopted from Peter Atkins' book that I just mentioned. There are 4 laws, and this is a very nice paragraph. So we have 4 laws, and the third of them, which is the second law. Okay, so you have, let me write it down. So you have 0, first and second and third. There are 4 laws. The third of them, which is the second law, because we start from 0. So the second law is the third one, was recognized first. So this one was identified first by Clausius, like I just mentioned earlier. And it has a very mechanical definition from the formulation of entropy. And the 0th law, this one, was formulated last. So this one is the first one to be discovered or discussed, and this one is the last one. And the first law was second. This one, the first law, again, it is the second one, and it is also discovered in the second place. And the third law might not even be a law in the same sense as the others, which means that the third law might not have the equal footing as these 3. So we probably cannot consider the third one as a law because it depends on the situation. It depends on how you treat your system and how you formalize your problem or your question. But basically, this is a very nice paragraph to show you like how people or scientists in the past discover these laws chronologically. And to discuss the 0th law, which is formalized last, is to talk about the temperature. In order to talk about temperature, we have to talk about system first, like I mentioned just previously. First of all, the system is isolated, or the term isolated here is not the isolated that we will use later. It's isolated from the surrounding. So we will have a boundary of some certain form to let us distinguish between the system and the surroundings. And add together, if you have system and surroundings together as a whole, it's the universe. So like the example like mentioned earlier, like the classroom is a system and you are the particles in this system. And outside this room will be the surroundings. And together, this is the universe. And from thermodynamics, from the classical thermodynamics, we can have 3 different types of systems. First one is the isolated. The second one is the closed. And we also have the open systems. And the difference between them, or difference among them, is the possibility of energy or mass exchange. So for the isolated system, the first one, 中文叫做那个孤立系统. Let me write it down in Chinese. For the isolated system, there's no energy exchange, and there's also no materials exchange or mass exchange, which means that it's completely isolated from outside. For the second one, we call this closed system, 或者封闭系统. For closed system, you can have energy exchange, but there's no materials or matter exchange, which means that the energy can flow into the system and can flow out of the system. So the energy of a system can be lower or increased, depending on the surroundings. We can have energy going into the system, or system can exert energy into the surrounding. So you can have energy exchange. But imagine that you have a lot of particles in the system. They will remain within this boundary. So the materials or the matters will remain in this system. So we call this closed system. And for the third one, we have open system. And open system is that you have a boundary, but although you have a boundary, you can have energy exchange, and you can also have matter exchange. So in a sense, if you have particles in within this boundary, the number of particles can be added from the surrounding, and it can also be decreased. And the particles can go into the surroundings. So basically, the definitions of these 3 are very clear, right? For the first one, there's energy exchange. There's no energy exchange. There's no matter exchange. And for this one, you start to have energy exchange. And for this one, you have the exchange for both energy and matter. So the definition is pretty clear. And for the zeroth law, the statement is like this. So if system A, which should be a closed system, is in thermal equilibrium with B, So imagine that you have two systems, A and B, if they are in thermal equilibrium, and B is in thermal equilibrium with C, then C will be in thermal equilibrium with A. So this seems to be very stupid, but this is the basics of how we define temperature. So if A is in equilibrium with C and A and B, then we know that B and C will also have the same equilibrium state. And in order to define that, we know that we need a physical quantity to define thermal equilibrium. And that thing is a temperature, which means that I think most of you in the general physics course or chemistry course have already learned this, that if they are all in thermal equilibrium, then it means that they have the same temperature. So that's the physical quantity that we want to define. So the temperature means that if these systems are in thermal equilibrium, then they all have the same temperature. So it's a thing that we can define. For instance, if one system has a higher energy or higher temperature than the other, we know that if we put them together, the energy will flow from the higher temperature part to the lower temperature part. So it's a thing that you can compare. And more importantly, from the definition, is that it's a thing to judge the systems are having thermal equilibrium or not. So when we talk about temperature, if we start from this definition, it means that it's not just like a scale bar to measure this thing is having a high temperature or this thing is having a low temperature. It's a physical quantity that allows you to compare the amount of energy in these two systems or in various different systems. Okay. And I believe that most of you already know that we have three scales. We have the Celsius, which is the most common one, at least for us, not for people from United States. They're using Fahrenheit. And for our scientists, typically we will use Kelvin scale. That means 0 will be the absolute 0 or the ideal absolute 0 temperature. And the room temperature will be at around 300 Kelvin. I think all of you have already know this. But then how was the Kelvin scale defined then? Because like I just mentioned, for the 0 point over here, it means absolute 0, 绝对零度. But how can we define that point? Like how do we know that this point is, say, minus 233 degrees Celsius? How do we know that? And that turns out to be from the experiment. We will talk about that in 20 minutes. 我们先下课吧. So basically we just saw these three different scales. And we know how we define this scale, right? The Celsius. The 0 is where water freezes, and 100 degrees Celsius, you get a boiling point of water. So it's defined by water at 1 atm. So, but for Kelvin, the scale is defined by a different way. Or to rephrase the question, like how low can you go down to lower temperatures? And that's also what scientists have been pursuing, because the lower the temperature you can go, the higher the possibility that you can liquefy some light elements, for instance, like helium or hydrogen. Those elements are really, really hard to liquefy. But if you can go down to lower temperatures, or typically what we call cryogenic temperatures, you can liquefy those materials. So how low you can go? And from Charles' law of volume and temperature, we know that you have this kind of linear trend. So basically, we know that from Charles' law, although it's called Charles' law, it was the experiment was done by Monton, which is a French guy, and he discovered that the volume of a gas will be linear to the temperature of the environment. And so basically, you can do an experiment. You can confine a certain amount of gas, and then you cool down your system, say by putting more ice around this a bunch of, for instance, gas molecules. And you start to measure the size change of this bunch of gas molecules as a function of temperature, and they found a very linear trend. Okay. Say, for instance, this is done at around, say, room temperature at 300 degrees Celsius, for instance. And you have this kind of linear trend. And these are the points you have, perhaps. Maybe 4 points. Then you can extrapolate, right? And see when these two lines will cross with each other. And that's a point when this volume ideally will go to 0. And from that, you can define a temperature point that these bunch of gas molecules have no volume at all. It seems that there's a critical point over here. And they can do this kind of experiments on several different gases. For instance, if this is, say, oxygen, you can do that with nitrogen. And for different gases, you'll have different lines. And interestingly, they all converge onto the same point, or roughly. I've never seen the real data, but I believe it won't converge to exactly the same point, especially when you were doing this experiment at around, say, 17th century. You won't get this kind of good data. But nevertheless, you will be able to see that there must be a point that volume goes to 0. And for different materials or for different gases, they all seem to have a very similar conversion point. And that point is at around minus 273 degrees Celsius. I believe that most of you know this as the 0 Kelvin on the Kelvin temperature scale. So that's how probably the lowest point that you can go from the extrapolation of this experimental data. And again, this is what we call the Charles law, 查理定律. I think this is probably what you will also learn in the first chapter of this in the textbook. So basically, you can do classical thermodynamics even if you don't believe in atoms. So the concept of atoms comes very late, after, long after the establishment of thermodynamics. So you don't need the concept of atoms to help you understand thermodynamics. But if you have the concept of atoms or those microscopic particles, it will be much easier for you to imagine like what's going on inside. So if you look at at a microscopic level, you'll see that, for instance, a bunch of ideal gas molecules or particles in a box, basically with a certain energy, or we say a certain temperature, these particles will just be moving around inside this box. And you'll see that some of them are moving faster than the others. And of course, some of them are moving slower. And it seems that it should have some certain distribution. So this is the microscopic view of what those gas molecules should look like. So if you cool down to 0 temperature, ideally there should be no movement of those particles. They would just be frozen in space. And that's the reason why we'll say it should have a virtually 0 volume, because they are not moving around, so you cannot define a particular volume or space for them. And based on the concept of microscopic particles, Boltzmann, you'll see that this is a very famous formula he derived, which describes the entropy as a function of multiplicity, or the numbers of possible combinations of the particle configuration. So S equals K log omega is probably one of the most well-known equation in thermodynamics or in statistical thermodynamics. And with the concept of particles in mind, then you can define the temperature or temperature scale in a different way. So for instance, previously, without knowing the particle nature of materials or the particle nature of, say, gas molecules, we can already, figure out Charles' law by doing this kind of experiment. However, if we have the concept of a bunch of particles occupying different energy levels, then we can define temperature in a different way. For instance, we know that if the temperature is higher, you can imagine that these particles, more of them will be having higher energy, and they will be moving faster, so intuitively speaking. So that's the picture over here. If the system is cool, then you'll have more particles in the lower energy levels. So many particles are, they are not tend to move around that quickly, so they're just in the low, they will be reside in this low energy state. But if you heat up your system and the temperature is higher, then you'll have more and more particles going into the higher energy levels. So this occupation of particles among different energy levels seems to tell you how high or how low the temperature is. So if you can define the distribution of particles as a function of energy, then there's a different way to define, to define a temperature of the system. So this is how we introduce statistical thermodynamics by looking at the statistics of particles and their energy distribution. The population of state of energy, for instance, if you have a particle at some certain energy level, for instance over here, a certain energy level E, and you can define the population of state of energy over the population of state of energy at 0, and we'll say this will follow this exponential term. And this is from the observation of this curve over here. So, for instance, if you have more particles here, then it means that the value of this, sorry, I have to go back and forth. This number is bigger. However, if you're in this state, this number will be smaller. So it seems that this ratio can define the temperature of the system. So let me put this more clearly. So using the same picture that we saw in the previous slide, for instance, we only have like two energy levels, say 0 and E. And we have a particle distribution like this. We have more particles at 0 energy state, and we have perhaps only 2 particles at a higher energy state. Then let's say P of E. According to Boltzmann, this should follow this rule. This should be an exponential decay. So, for instance, something like this. So if you plot population of E as a function of E, then it's an exponential decay. Or, if you want to look at this in a different way, you can rotate this by 90 degrees, and there you go. You have the regular function type. Almost the same though. So typically, you have more population at a 0 state, and you have less at a certain energy level. So for instance, here, this is, let's say, 6, and this is 2. So this is 1/3. However, if you're in a higher energy state, then, for instance, 2 more particles are excited to here. Then, in this case, this becomes 4, right? You have 4 over here, and here is also 4. Then this becomes 1. And we know that this represents cold. This represents hot. So it means that this number somehow can also provide us some information about temperature. And we can define temperature, from this variation of this ratio. So it turns out that the beta over here, this prefactor in front of energy, is the inverse of temperature. It's the inverse of the temperature. So this one is kBT over 1 over kBT. So it means that if the temperature is higher, then this ratio, this beta term will be smaller. And that will automatically adjust the numbers of population or the particle population for you. So you don't have to worry about like at what temperature, like how many particles will be there. This will directly define that for you. So the bottom line is that if you have a function like this, let me write it over here. Let's say now we have this. So if we have this, then we can define the temperature of the system by looking at the occupation of particles, for different, at different energy levels. So the distribution of particles among different energy levels will define the temperature of the system. So we will come back to this when we talk about statistical mechanics in more details. But please keep in mind that temperature can be defined by several different ways, and I've already mentioned two of them. The first one is from the the volume, the change of the volume. That is what we call the Charles law. And the second one is from a microscopic point of view, that we use the population distribution of particles among different energy levels. So these are the two ways to define temperature scales. And interestingly, this is actually a better temperature scale, which is inverse of the regular temperature that we know. So in fact, a better temperature scale is 1/T. So if you read Peter Atkin's book, he will tell you that beta over here is in fact the best temperature scale. But we already know that like if you have a very, very high temperature, for instance T is close to infinity, then beta is 0. This is fine. But when T is close to 0, this is close to infinity, which is a singularity term. So this is not a very good definition based on our intuition. But based on theory and physics, this is a better temperature scale. And from that, you can start to see many interesting things. For instance, we've already mentioned that you can do classical thermodynamics even if you don't believe in atoms. For instance, the things that you are going to go through, basically you don't have to understand, you don't have to believe in atoms at all. But if you look at microscopic level, you'll start to see something interesting, and also the Boltzmann distribution that I just mentioned. More importantly, and you'll start to see some counterintuitive phenomenon that only can be seen or can be defined by using the definition I just used. Population inversion and negative temperature is an example that normally, if you use a classical thermodynamics, there's no such thing as a negative temperature. But if you're dealing with, say, microscopic view, and you use this formula to define temperature, then you will see a negative temperature when you have a population inversion. And population inversion is a very common, I would say, phenomenon that when you have lasers, for instance, inside this laser pointer, you have this excited states. So regularly you have normal distribution, like I just mentioned. You have more particles at a ground state. You have less particles in the excited state. However, if you can somehow pump particles to excited states, and you have a temporary population inversion, which means that you have more particles at a higher energy level, then by this definition, then you will get a negative temperature because the number will be greater than 1, right? So regularly, you get, for instance, a number that is less than 1, which is, say, 1/3. And this is the case I mentioned earlier. This is hot. And in that case, you have equal numbers of particles at 0 and the excited states. But imagine that you have one more particle going upward, and you have 3 over here and 5 over here. Then this number will be greater than 1, right? And if this number is greater than 1, then it means that beta has to be negative, right? Otherwise, when this is 0, it means that beta is 0, and t is infinity, right, in this case. But if you have a number that is greater than 1, then the temperature should become a negative number. Beta should be a negative number, and therefore the temperature will also be a negative number. So if we follow this definition, then we will start to see that the temperature using our old standard scale will become negative when we have a population inversion. Here it has a three-level case, but it's much easier to understand if you use a 2-level model, because then you'll get this concept very easily. And like I just mentioned, population inversion is very useful for getting laser, because you first excite particles to higher energy states, and they will relax and go back down to the ground state, and then they will have a coherent emission of photons. And that's why we call the laser, right? It's a light amplification by stimulated or the emission of radiation. So this is the working principle behind laser. And more importantly, here you start to see some weird examples that the temperature based on the definition of population distribution will have, for instance, a negative number, like we just mentioned. And more importantly, we have this Maxwell-Boltzmann distribution of particles. Again, if we go back to the microscopic view of, say, the ideal gas being confined in a certain space, then we have a distribution of velocity for these particles. And from the statistical mechanics or statistical thermodynamics, they can derive this kind of formula that the distribution of velocity will be dependent on the temperature of the system. So how hot the system is will determine the distribution of particles. If you have higher temperatures, then the distribution will be more spread out, and you have more particles with higher velocities or higher speeds. And if the temperature is low, then of course you have more particles at lower speeds. So this is sort of consistent with what you learned in high school, right? That I'm not sure if you have derived this in the high school or in the general physics or chemistry class, but these are a very common expression for the distribution of velocity for the particles in a certain under a certain temperature. Okay, so these are just some concepts for the microscopic view of temperature, or how you can define temperature using different ways. So again, first of all, we have the Charles law that we mentioned, and then we have the occupation expression, which will lead us to the weird result of, for instance, negative temperature. And then we can also look at the distribution of the velocity for all these particles you have. And in fact, this distribution should be consistent with the energy distribution you have in your system. So for instance, for the ideal gas, you will always have only the kinetic energy, and you don't consider the interactions or the potential, energy among the particles. So you only have the kinetic energy. So if you convert these into energy terms, later we will see that for ideal gas, the energy, or the internal energy, will be 3, this is 3 over 2 times kBT. So it means that the energy of the system of these ideal gas particles will be proportional to the temperature you have. Okay, so that's what we're going to go through very quickly, I think, for this lecture. I think this is the end. So that's the zeroth law. So what we just covered is some basic concepts of temperatures and how we define it using different ways. And next, we're going to talk about the first law, which is the conservation of energy. And this is very straightforward because the 4 laws of thermodynamics, basically, I think the most important ones are, I think the zero law typically won't show up in your exam. And the first law and the second law might be the most frequent ones that you will encounter. So basically, the first law is probably the most important thing that you have to get used to it, or to memorize it, or whatever you want to do it. Just remember how to write down the first law. And basically, it's just the conservation of energy. So I mentioned many times the energy. But in terms of energy, there are many different forms. We have energy. It's a very general concept. Anything that's in units of, say, joule, or like how many calories you have, you can say that's energy. But there are different forms of energies. For instance, heat and work. Although in terms of units or in terms of dimension, there are both energies. But in reality, they are in very different forms. Let us look at work first. So let us consider an adiabatic system. The adiabatic here, which later you'll see in your textbook, means that it's thermally isolated. So just consider it as an isolated system. And if we have a thermodynamic process, start from the state A and state B, we don't have to worry about the definition of terms right now, which we will go into details later. Just imagine that you have an original state, which is called A, and later, the system was evolved to B. And from A to B, imagine that the energy has become higher when you go from A to B. And there are different paths to go from A to B. So you can go along this line, the red one, the blue one, or you can go along the straight lines and then go up. So all paths between A and B, so either you go from here to there using path 1, 2, or 3, they all require the same amount of work if the force is a conservative force. So perhaps this is too abstract, but if you remember that when you learn classical mechanics in your general physics course, you learn about the concept of potential energy, right? And a general consensus is that if you start from A and you move out your particle to a position that is higher, and the only energy that you need will be to overcome the potential energy, right? And you raise your particle from for instance, from here to here. And the only difference is the height. So the potential energy in that sense is mgh, right? And h is the difference between the two locations, or the height difference between these two states. And we know that the force is a conservative force, which is coming from the gravity, and it's always pointing along the same direction. So that's the reason why the work of this force is only acting, along this direction. If we are talking about gravity. So all paths between A and B require the same amount of work if the force that we were enforcing on the system is a conservative force. And this is the example from Peter Atkins' book, that we can go from path 1, along path 1 or along path 2. And we know that path 2 is longer. But in terms of work, or the amount of change of, potential energy, they are the same. And they are the same. So this is probably the first definition of work that you will encounter when you learn classical mechanics. So again, the work required, in fact, is just the final potential energy minus the initial potential energy, which is, in this case, or you can say delta U, delta H, if you still remember this. However, in classical thermodynamics, we typically don't use the term potential energy. We use internal energy instead. And we use the same notation, which is capital U. So it is internal energy. And more importantly, it's a state function, which is similar to the potential energy that we used in classical mechanics. If you remember from classical mechanics, again, this potential energy is defined by the height or the location of the object. But if you move your object horizontally, basically it won't change its potential energy. And from that, you can define a certain state, for instance, which is the height of the object. And that's the same for thermodynamic internal energy. It's a state function, so you can use internal energy to describe a state. For instance, it's a state function for volume and temperature, just for instance. So that's the concept of internal energy. And then, this is the famous Joule's experiment. And I don't know if you still remember, but I believe you learned this when you're in perhaps high school or in the freshman year, that this experiment is actually trying to demonstrate that the connection between heat and energy, or you can say heat and work. So basically, they have the same energy, the same format of physical quantity, which is energy. So the experiment is very straightforward, that you have a weight which can convert, the let's say the potential energy into kinetic energy, and this turbine over here inside this box of water will start to rotate and will agitate the system. And ideally, if this is a completely isolated system, it means that if the energy won't spread out or dissipate into the surroundings, then the kinetic energy will be completely converted into the kinetic energy of water, and that will heat up the system. So if you can measure the temperature change of the water, of this system, then you can convert that into the, you can figure out the equivalent work being done over here. So by looking at the temperature change over here, then you can calculate how much work has been converted into heat. And again, heat and work, they are all in the format of energy, but in terms of measurement, the complexity is very different. For instance, for the work, which is the height difference before and after the process for this weight over here, it can be easily calculated by this formula over here based on classical mechanics. But for the energy change over here, which is in the format of heat, you have to measure the temperature change. So this is a very classical design of experiment to link the connection between classical mechanical energy and heat, which is a thermodynamic energy. And it was designed by Joule back in the early 19th century. So here's another schematic illustration that probably you will see, or you have already seen back in high school, that originally you hand a weight over here, and then you release it such that it will move down, and that will drive the turbine over here. It will start to rotate, and will transfer this kinetic energy of this turbine to the water. So ideally, if there's no heat loss, into the surrounding, you'll start to measure a very obvious temperature change inside this water system. But that's the case when you have a very, very well isolated, I would say, insulation layer. So that's the difference between these two figures. For this one, the energy will dissipate to the surroundings, which means that it's based on the definition from our last lecture, it's a closed system. So you can exchange energy with the outside, with the surrounding, but of course the water, these molecules will still be confined in this container. In contrast, if you're dealing with this system over here, it's an isolated system. So the energy will be confined in this container. So it won't go out. So that's the difference between these two figures. So that difference is the energy transfer as heat. So if you measure the temperature change of these two systems, then of course you'll see that in this case, the temperature change is larger because all the energy from the work done over here is transferred to the water. However, if you're dealing with the right-hand side system, you'll see that a lot of heat, a lot of energy will be dissipated into the surroundings as a format of heat. So that's the reason why we have a remark over here. The difference is the energy transfer as heat. And in this case, then, when you measure the temperature change in this water system, you'll see that the difference is smaller, right? The temperature raise won't be that large because part of the energy has been converted to heat and it was absorbed by the surroundings, because this is not a fully isolated system. So the statement of first law of thermodynamics is that the energy is conserved. Okay, the energy is conserved, but they are divided into two. You can say 2 or 3 different categories. So you have the heat part, you have the internal energy part, and you have the work part. So the first one is what we call heat. And that's the part that we just mentioned that's being dissipated into the surroundings. So to be more specific, typically you'll see this kind of plot. So this is the system you have. And you have the work, coming into or out of the system, or that's the work over here. And you also have the change of internal energy that can be done by increasing temperature of the surrounding or decreasing the temperature of the surrounding. That's being influenced by outside. Then you also have the change of heat over here. For instance, let's say we have du over here, and that's being controlled by, let's say, the dq here and the dw here. This is just a general expression of how we describe the first law of thermodynamics. That like we just mentioned earlier, internal energy is a state function, so it can describe the state of the system. So I typically write this inside the system. And heat is some energy form that can be dissipated into the surrounding. So you have something like this. And the work can either be done by the system or done on the system. So it can also have these 2 directions. So depending on the definition of work, sometimes you'll see different definition of first law. So for instance, right now we have an expression like this. You'll see that I put a hyphen over here on the D, which means that sometimes this is not, for instance, the work, if it's not conservative, then we have this is not a perfect or exact differential, then we put a slash over here. And this expression is, or the expression on the screen, is consistent with the expression on your textbook or in your textbook. But in some textbook, for instance, if you look at, I don't know, for instance, in your general chemistry class, perhaps you will see a different sign over here. I'm not sure what kind of expression you saw before. And the reason why you have plus sign or, not, or minus sign over here is because we have different definition of the work difference over here. Sometimes we can define the work done by the system as a positive sign, but in some cases, in some books, the definition is the opposite, that the work done onto the system will be defined as a positive. So then you'll get a negative sign in the expression over here. So basically, over here, the change, we realize that the change of internal energy will be determined by the change of heat or the change of work. Or you can see this in a different way, that if there's no heat dissipation, in the case of the isolated case, the work will be completely converted into the change of the temperature. So du will be minus dw. So the work you down to the system will be completely converted to the change of internal energy. So the temperature of the water will be raised, right? So in this case, then we realize that the dW, by this definition, is the work done by the system. So if you use plus sign, then the dW here is, let's say, work done by the system. And if you see a negative sign, so if you see something like this, then it means that the first law in that book is determined by the work done on the system. Or we can say done onto the system. So do realize that the difference between these two. But if you don't want to worry about that, just keep in mind that for this semester, for the book that we're going to use, we're going to use this convention. So we're going to use plus sign between the difference of internal energy and the work. So at least when I was in undergrad, I just directly memorized this. I didn't care that much about the work. So I was very lousy at that time. So, but if you want to be careful or to know why there's such difference, this is because one of them is defined as the work done on the system, and the other one is done by the system. Okay, so that's the two. That's the major difference. And we'll come back later to talk about the difference between work and heat. 好，我们先到这边。So what we saw over here is that the connection between internal energy, internal energy of the system, the heat, and the work. And this is a state function for the system, and these two are the energies that can be enforced onto the system, can be flowing into a system, out of the system, but in different formats. For instance, the work I mentioned, according to previous slide, is the movement or the release of potential energy from here to here. And the heat, on the other hand, is this dissipation, right? This dissipation. And the internal energy change will take place inside the system of water. So one major difference between work and heat, which is very important, because I believe in most of the books, they don't tell you this. They just give you, they just assume that you know what's the difference between work and heat. But I believe most of you are, most of us don't understand it that much. So a clear picture to tell you the difference between these two are shown over here. So you have the surroundings, and you also have the system. So imagine that the surroundings have a lot of molecules, and when the system, for instance, is enforcing a work onto the surroundings, it means that the energy is being converted into some sort of uniform motion. So the work is the transfer of energy that makes use of the uniform motion of atoms in the surroundings. So for instance, over here, we see that the uniform motion is the drop of the weight from a higher place to a lower place. Right? This is a uniform motion. And in some cases, in later cases, we'll see heat engines. And in some heat engines, you have pistons, 活塞. These pistons, they'll move around and they'll compress, the gas molecules inside. And during this compression process, we're enforcing work onto the gas. And because we're pushing them along the same direction. So that energy form will create a certain amount of uniform motion of the atoms or molecules in the surroundings. However, if you're looking at heat, we're also transferring energy, for instance, from the system to the surroundings. But if the energy is in the format of heat, then you're just creating a random fluctuation of those atoms. So heat is the transfer of energy that makes use of the random motion of atoms in the surroundings. So again, go back to here. If the energy is dissipated into the surrounding, then you'll start to see the surroundings start to become, say, hotter and hotter. And that is because the energy will cause more random fluctuation of the gas molecules in the air, right? So the heat will cause random fluctuations, while the work will give you a uniform motion. So that's the major difference between using work, or say describing work and describing heat. And this is a very interesting remark when we talk about heat and work. Again, this is from Peter Atkin's book, so you won't see this kind of interesting remarks in your textbook. The molecular interpretation of heat and work elucidates one aspect of the rise of civilization. So it is related to how we build our civilization. We know people use fire, right? At the very beginning of at the very inception of humankind. But we don't know how to use work until very recently, at the time of Industrial Revolution. So that's, say, I don't remember, 17th century or 18th century. So that's very late. So fire preceded the harnessing of fuels to achieve work. And the heat of fire, the tumbling of energy as a chaotic motion of atoms, is easy to contrive, for the tumbling is unconstrained. So the bottom line is that using heat is simple. It's much simpler than using work. In order to harness work, this kind of energy form, you have to design some certain type of machinery in order to allow you to harness that kind of energy. So work is energy tamed. Tamed means 驯服, okay, and requires greater sophistication to contrive. So the humanities stumble easily onto fire. You can easily just start fire, right? Not for us, but for ancient people. They know how to start fire very easily. But needed millennia to arrive at the sophistication of the steam engine. So that's several centuries later. I think, who was the inventor? Watt, maybe? He invented steam engine. And then we can start using work to use this kind of special form of energy term to let this energy work for us. The internal combustion engine and of course the jet engine. I mean, these more and more sophisticated design of machinery allows us to use energy in terms of work rather than using heat. So we know that heat is pretty much useless, right? It's almost unwanted in many systems. You want to reduce the generation of heat. For instance, if you use a computer, we know that the CPU will generate a lot of heat waste. And if you can further reduce that, you can increase the efficiency of computation. So for a modern point of view, heat is pretty much useless in almost all the systems that we're using. And in fact, when we talk about efficiency of any kinds of machinery, we're talking about the ratio between these two things. Basically, we want the heat to be as small as possible, such that we can have the maximum work when you have a certain temperature difference. So that is related to the second law of thermodynamics. Although right now we're just talking about first law over here. But the interplay between work and heat will be strongly related to the second law of thermodynamics. So again, this remark is very important. Although not important for you to get higher grades, but it's important for you to understand the physics behind, or the basic principles behind thermodynamics, and especially the meanings of these three things. Okay, so when we talk about process, for instance, at the very beginning, I mentioned that you have a system evolving from state A to state B. And this evolution from A to B is what we call a process. For instance, we can heat up the system and then such that the volume of the system will become bigger. Or you can cool down the system such that the system becomes smaller, the volume of it becomes smaller. Or you can control the volume and then increase the pressure. And this is what we call the process. And there are two kinds of processes in thermodynamics. The first one is reversible process, which is very rare because in reality, probably there's virtually no reversible process. So this is one good thing to learn thermodynamics, that to understand that the arrow of time is always pointing forward. There's no turning back for you. The things you're doing right now will determine the path of your future. And it is not reversible. Okay, this is kind of, how to say, miserable, but it is indeed the nature of our universe. Everything is almost everything is irreversible. But in theory, we can still discuss reversible process, and I believe that's what most of the textbook will be about, because only for the reversible process that you can do some easy calculations. So that's the reason why typically we will focus on reversible process first. And for reversible process, it's a change from initial to final state by an infinite number of infinitesimal changes. So if you went through calculus during the freshman year, then you know what infinitesimal means, right? It means it's very, very small, and it's smaller than the smallest thing that you can imagine, and which means that it's almost impossible to have that kind of variation. It also means that to achieve this kind of process, you have to take almost an infinite amount of time. So you have to take a very, very long time to get from state A to state B. So in reality, we know that this is almost impossible, unless this process is taking an extremely long time, like similar to the span of a life of the universe. But that kind of process is pretty rare. So we know that it can be cut into very, very small steps, and it's an evolution that is very, very small, and it can achieve the maximum work. So later we'll see this in, I think, when we talk about the second law of thermodynamics, that the reversible process can give you the maximum work. Again, this is related to these things, especially dq and dw, the heat and the work. We want to minimize the produce of heat, and we want the maximum produce of work. So in order to achieve maximum work, we have to go through a reversible process. So if you're dealing with irreversible process, then you know that you will get a greater heat waste. So for a reversible process, you change from initial to final state, for instance, state A to state B, by a finite number of incremental steps. So for instance, if we go back to that example that we drew, that we show in the first slide, we know that there's state A. I should write bigger. And the state B. And if you still remember, we have a path like this. So imagine that for this, so this is path 1, this is path 2. So for path 2, it can be divided into 2 steps. So just 2 finite steps. But for this one, if it takes a infinite long time, then we can divide this into very many small steps. Then we can call this a reversible process. And in contrast, this one is an irreversible process. So when people typically draw this kind of plot, they will say, okay, so this is a smooth curve, so this can be considered as a reversible process. But it really depends on how you formalize your problem, or what the question or the problem provides you. Because even with this kind of path, the problem can say, we have this kind of path, but it is a reversible process, which means that it can be divided into many small steps, and they can be combined together into a reversible process. So it really depends on how the problem set or how the question provides you. Okay? But most of the time, you will be dealing with reversible process because, again, like I mentioned earlier, you can calculate things based on reversible process. But for irreversible process, it's typically hard to do some math on it. And if you are dealing with irreversible process, then you have less work be done. And if you go back to the mechanical example that we mentioned earlier, this one, imagine that this is not a when you perform this kind of process, if you push this particle up to the hill, if this is not a conservative force, which means that if you include friction, into the system, then the process will need more work to move the particle from here to here, right? And at the same time, when you push this particle uphill, you will generate heat because there's a friction between the particle and, say, the mountain you have over here. So it will start to generate heat. And you will have more dissipation than dealing with a purely conservative force system. So in that sense, you have less work being transferred onto the particle. So that's the reason why here we say if you're dealing with an irreversible process, then less work can be done. And you will have more heat waste. Imagine that, let's say, we have, actually we should use the convention that the textbook tells us, which is a plus sign. And we can move these things around. Let me say something like this. And we know that if we want to show that this is the work done, say, right now, this is defined by the work done by the system. But if it's done on the system, then we have a plus sign over here, right? And if we have more heat, if we have more work, then it means that we will have less heat waste. However, most of the time, if you're dealing with irreversible process, you have less work can be done, and therefore you have more heat waste. We'll go into more details when we talk about the efficiency of a heat engine. So just keep in mind that there are two kinds of processes. And similar to what we will go into during the first chapter of our textbook, we will introduce a different kind of energy calculation method, which is the concept of enthalpy. And the enthalpy, from the definition of the term over here, it means that it's the heat inside. So the enthalpy typically is represented by the capital H. H is U plus PV. And this is also a state function, depends on the process of the evolution of the system. And it follows that if we're interested in the heat that can be generated by the combustion, especially for combustion of fuel, in an open container, for instance, like a furnace. And the reason why here we talk about furnace is because then when we burn something, the atoms or the gas molecules are free to be released into the open space. For instance,
if you have a container, let's say a furnace, you have, say, some fuel inside. And you are burning these fuels, trying to generate some whatever, some work or whatever you want to generate. And if the temperature is high enough, we know that the fuel will start to evaporate. And the gas molecules can be released into open space, right? So that's the reason why in the typical conventional power plant, you will see this kind of furnace and you have smoke coming out from it because you are burning the fuels in order to generate energy. You are releasing the energy that's being confined in the fuel. So in order to calculate the energy that's being released, or originally is being confined in the fuel, we use this kind of new type of state function, which is the internal energy plus the product between pressure and volume. And we use tables of enthalpies to calculate the change in enthalpy that accompanies the combustions. So typically, when you encounter a problem of, which involves delta H, or the change of enthalpy, it is related to combustion, 燃烧. Okay. So during the first two chapters of the textbook, you will see a lot of calculation of delta H. And also in the later sections, later chapters, I think chapter 5, chapter 6, when we talk about the phase change of solids, we'll also need to calculate like the change of delta H. So this uppercase, this delta, I think most people know that the delta means the change or the variation of the quantity, so we don't have to go into details. But the calculation of delta H is, it plays a very important role for the next, say, 2 or 3 weeks of this semester. And typically, I think when you go through the general chemistry or general physics course, whenever it talks about thermodynamics, you'll see this kind of plot that talk about the reaction of, or the release of energy or heat during the chemical reaction. So this is an exothermic reaction, which means that it releases energy when it comes from the left-hand side of the equation to the right-hand side of the equation. In thermodynamics, the term exothermic process, exo means outside. It's a very common expression for the process that we will go through. Describes a process of reaction that releases energy from the system to its surroundings. So when you put these together, and of course at the very beginning you have to overcome an energy barrier, which is called the activation energy. Then the reaction will be started, and you start to release the energy in the form of heat, and then you get your products. Then this form, this heat, can be calculated by the difference of enthalpy. So, which means that the heat over here, originally written as dq, in this case, can be written as delta H. So over here, so typically we start from here, we have But in this case, when we talk about chemical reaction, or typically in the case of combustion, the heat change is delta H. So in this case, the enthalpy change is the change of heat, or the heat being released or being absorbed by the surrounding. And another term, another physical quantity that you will encounter for the next few weeks is the heat capacity. So the heat capacity is defined as dq over dt, and T over here is the temperature. So it describes the capability of a system that can absorb heat or release heat. And it's a slope of the slope of a graph of the value of internal energy plotted against temperature is called the heat capacity of this system. So we can describe by how much how much energy the system can absorb using a plot like this. Let me show. Don't know if I have the plot over here, but later we'll see that this heat capacity is defined as, say, dq over dt of a certain system. For instance, for a solid, you'll see a very typical curve like this. So as the temperature increases, the heat capacity will saturate at a certain value. So although the system can still absorb heat, but the rate of heat absorption is already saturated. It's already saturated to a certain value. And the capability of absorbing heat will decrease when you go down to, say, 0 temperature. When you go down to cryogenic temperatures, the capability of absorbing heat or releasing heat will become smaller and smaller. So that's the reason why it is really hard to get down to 0 temperature, because it is hard to further extract heat out of the system. Because the heat transferring efficiency of the system is gradually getting lower and lower. Okay. So this is another physical quantity that we will discuss a lot during this semester, and it's typically, it's called heat capacity, and the symbol is C, for instance. And it depends on the process you have. So later on you will see Cp or Cv. Depends on the process is constant volume or constant pressure. So you will see two kinds of notations. And this means that the process is constant pressure. And this one means that it is constant volume. So we have two kinds of processes. Two kinds of heat capacity that we want to discuss. One of them is the process is under constant pressure. The other one is constant volume. And we'll see the connection between these two, especially for ideal gas. It can be mathematically derived. And you'll see that substances or materials with a high heat capacity, for instance, water, we know that water is a high heat capacity or high specific heat material, require a large amount of heat to bring about a given rise in the temperature than those with a small heat capacity. For instance, air is an example for a small heat capacity material. Which means that when you look at this definition, so we know that C is, let's say, dq over dt. If this is fixed, if you have a certain amount of heat that's being transferred into the system, if you have a large heat capacity, then it means that the delta T will be very small, right? If this is fixed, if this one is large, then delta T is small. For instance, like water, you have a large heat capacity. So for a given amount of heat being sent into water, you have a small change in terms of temperature. However, if you're dealing with a small heat capacity material, then the delta T will be large, even by sending a given amount, like small heat into the system. For instance, like metal, the heat capacity is typically lower. So when you have a small amount of, say, heat going into the system, you can cause a large temperature change. So that's a concept. That's the concept of heat capacity. And we know that if you divide this by the total volume, which we will later be more elaborated, we can define a new term which does not depend on the size of the system, and it's called a specific heat. We'll talk about that later next week. So here, to be almost precise, the heat capacity is defined as here over here, heat supplied over the resulting temperature rise. So this can be experimentally done. You can measure the temperature change by sending heat into the system. And the supply of 1 joule of energy as to heat 1 gram of water results in an increase of temperature about 0.2 degrees Celsius. So if I just go through these numbers, it seems that because you have no sense of what 1 joule of energy is, but this is how they define these terms. Now, for instance, if you put 1 joule of energy heat to 1 gram of, say, aluminum or copper, then you should expect a much larger change in terms of temperature. For instance, 10 degree or 20. I'm not so sure, but I believe that it will be much greater than 0.2 degrees Celsius. So here they're just trying to show that the temperature change of water is typically very small. And that's the reason why we say the ocean is a good regulator, because it's a very, very large heat sink. So it's hard to change the temperature of ocean because it's a huge amount of water, and the heat capacity of water is also very large. So in formal thermodynamics, the condition under which heating takes place must be specified. So the reason why it needs to be specified is because for these two things that I mentioned, it depends on the process that you go from one state to the other. It can be under constant pressure process. It means that the sample is free to expand. Then some of the energy supplied as heat goes into expanding the sample, and therefore doing the work. So the constant pressure means that, for instance, you're having a piston. So here you have a confined space, and imagine that this valve can move around. And if you heat up the sample, not the sample, we heat up the system, and you know that the gas molecules here, the total volume of it will tend to increase, right? So if you fix the pressure, which means that the pressure here, say if it was kept at 1 atm, then the volume of this gas will start to increase because you keep supplying heat or energy into the system, and that can be converted into work. So this piston will start to move up. So the volume will increase. And the pressure is a constant. In this case. Okay, in this case. So this is the constant volume process. And however, if you want to confine the gas molecule such that the volume is fixed, then you can make this part fixed, right? And then this piston it won't move around. Then in that case, if you heat up your sample, heat up your system, the pressure will build up because the volume is fixed. And we know from previous lecture that if you heat up your system, then the gas molecules will start to move faster. So it's hitting on the walls more frequently than its original state. So the pressure will go up while the volume is constant. So in that sense, you are getting a constant volume process if the volume is fixed. But typically, these are given, again, by the problem set. So they will tell you that right now we're considering a reversible process under constant volume condition. Or if it's a free expansion, it means that it's a constant pressure, then the volume is free to increase or decrease. So it depends on how the question is made. So less energy remains in the sample, so its temperature rises less than when it's constrained to have a constant volume, and therefore report that its heat capacity is higher. So the paragraph over here is trying to explain that the difference between constant pressure and constant volume heat capacity. So imagine that if you're using a constant pressure condition, then it means that, again, this part is free to move. And when this part is moving, and you start to have a uniform motion of atoms acting on the surroundings, right? The outside. So we are doing work. And the work is along a very uniform direction. So it means that you are creating more work than the constant volume process. Because for the constant volume process, the total volume is fixed. So when you heat up the system, the gas molecules are just moving faster without doing any extra work. So the paragraph here states that less energy remains in the sample, so its temperature rises less than when it's constrained to have a constant volume. Please go back and read this paragraph again to get a clear understanding of what it's trying to say. It is related to also the temperature in the system. That's the reason why it says here the temperature rises less than when it's constrained to have a constant volume. Because if you're free to move around, you create more work, but then you have less heat. And so overall, to understand the description over here, basically all you need is the first law of thermodynamics, this equation over here. And it depends on like how much work the system can do based on constant pressure or constant volume processes. If you don't understand right now, it's okay because we will come back to this again, I think in 2 weeks. Yeah, in 2 weeks. And the last remark for heat capacity is for every substance, the heat capacity will fall to 0 when the temperature is reduced towards absolute 0. And that's the plot I have over here. I've already told you that if you cool down your system, typically, not typically, I think for all systems, the heat capacity will go down. So, like I mentioned, it will get harder and harder to cool down your sample when you reach cryogenic temperatures because the heat capacity is so small. So even a tiny transfer of heat to a system results in a significant rise in terms of temperature. For instance, if you are right here and you're trying to cool down your sample further, but accidentally there's a heat or fluctuation coming from the surrounding or from the outside, and that will make a dramatic change in terms of temperature because the heat capacity is low. So over here, if you have let's say, let me write this way. Yeah, I think this is more straightforward, that if you write write it this way, then you know that if heat capacity is small, then even if you have a tiny amount of heat accidentally being sent into the system, you will get a large temperature change. So you will get really hard to cool down your sample when you go down to low temperature. So this is one of the problems associated with achieving very low temperatures. So even a small leakage of heat will cause a very large temperature change. And this is actually related to fluctuation dissipation theorem that we won't cover until the very end of this semester. So this is another example of heat capacity as a function of temperature. And this is an example from diatomic gas. So there's a gas molecule with 2 atoms. And so it depends on process condition, constant pressure, constant volume, that will give you different numbers. And microscopically, it is related to degrees of freedom. So if you have atomic gas, you have different, say, rotation modes or vibration modes. And originally, down at 0 temperature, you have the translation. Again, this is for the ideal case. So for ideal gas molecules, even when you go down to 0 temperature, you still have a fixed number for heat capacity. This is related to the internal energy of the system. That is (1.5 times kBT, right? We know that the internal energy of an ideal gas, if you just consider the translation energy or the kinetic part, is proportional to temperature and is proportional to kBT. I already mentioned this, but we haven't derived this yet, which we can derive by using statistical thermodynamics. But this is probably you've learned in high school, that they ask you to just remember, right? And that's the reason why at 0 temperature you still have 3/2 over here because it actually should be 3 kb/2. So because it is in this case, it is something like this. We just divide this term by temperature, so you end up with 3 kb/2. So that's the reason why you have a finite number. But in reality, like what was stated in the previous slide, that eventually when you cool down to low temperature, this should also go to 0. So this is for a theoretical prediction. You have this the number. Of course, when you heat up your sample or heat up this diatomic gas system, you start to see some different modes. So you gain some other degrees of freedom. Originally, these molecules, they are just moving around, right? They are just moving around. They have no, say, rotation or vibration. But when you go up to higher temperatures, maybe these molecules start to find that you can rotate. So that's the reason why, for instance, if you look at this molecule here or here, they are rotating. So you gain another degree of freedom. You gain another kBt. And why it is kBt, we will derive that later this semester. So you add another kBt here, so your capacity will be increased from 3/2 to 5/2, increased by 1 kBt. And if you further heat up your sample, then you have the vibrational mode. And for vibration, it is something like this. So you gain another degree of freedom, you gain another kBt. So you have another step over here. So you end up with 7/2. So that's the reason why typically people will say for different kinds of gases, you have different kinds of temperature dependence for heat capacity. Okay, so this is related to the microscopic behavior of this diatomic gas. So if you're dealing with single atom gas molecules, then you won't get the rotational mode and vibrational mode, so you will just get ideally you will just get a constant 3/2 because you don't have that extra degrees of freedom. Okay. And the heat capacity for solid, like I mentioned, is actually the cornerstone for solid state physics. So in the future, if you take solid state physics, typically this is a very important part that will definitely go through. And it describes the vibrational modes in the materials as a chain of atoms. So you can see that these are vibrational modes with different wavelengths. And depends on the temperature, the vibrational modes or the number of these kind of modes will also change, which in turn will change the trend of heat capacity as a function of temperature. So the classical theory, again, will predict that at 0 temperature you have a finite heat capacity due to this I just mentioned. But in reality, when you take, for instance, an iron or aluminum and you cool it down, you'll see this kind of trend. So later this semester, we will also go through this and to explain why we have this kind of behavior. So right on time. So for next time, we'll just go through, I think we will start from the first chapter of the book.